represent information in some form. And you're probably at least vaguely familiar with the idea of binary or bits. Somehow or other, computers reduced to zeros and one. But can we embrace that and at least put a bit of light to that? So I have these little desk lamps here. I have an electrical outlet here, and I'm going to propose that inside of my computer is at least one of these things, something capable of being switched on or off. In this case, it's indeed a desk lamp, but at the lower level, it's something called a transistor. But in our world, it's a desk lamp. So I'm going to go ahead and plug this into my electricity here. And I claim that using this simple device, this simple switch, I can represent information. For instance, right now, I am representing nothing, right? I'm representing what I'll call 0 or false, the opposite of something actually being present. But if I simply turn this switch, now I've represented a 1. So using this very simple piece of memory, if you will, I can represent information. Now, unfortunately, my computer can't do all that much. It can only represent 2 values in the whole world, 0 or 1. But what's an obvious solution now if we want to expand our computer's memory and represent more than just 0 and 1? Well, let's grab another such bit. Let's grab another switch, another transistor, however you'd like to think about it. Let me go ahead and plug this into my computer as well. And I'm going to claim now that by using a bit more electricity and turning more of these switches on and off, I can represent more such information. So right now this is 1. If I want to now represent 2, I could do this. But typically convention, as we'll eventually see, would have me do this. So this is 0. This is 1. This would be 2, and, not surprisingly, this would be 3. So in this way, still, can we count up even further? If I get a third bit, a third switch, what's the highest number I can now count up to from 0? So 6 if I'm starting at 0, right? Because if I turn this light on and actually plug this third and final light into my electrical socket here, then I have the ability to represent any of 2 values here, 2 values here, 2 values here. And so I can represent minimally now, I can represent 2 times 2 times 2, or 8 possible values. And if I start counting at 0, so that's 0, 1, 2, 3, 4, 5, 6, 7. So this is binary. It really is as simple as that. And I'd argue that this is actually quite familiar to most everyone in this room. Let me go ahead and open a little text editor here. And you might recall from grade school that we had things like the hundreds place, the tens place, and the ones place. And recall that if you had some decimal number, like something random like 123, you would essentially write that out in the form of these 3 columns. And y is 1, 2, 3. What we know is 123. Well, in the leftmost column, we have 1 100 plus 2 10, so that's 120, plus 3 1, so that's 123. Now, this world that we just illuminated is exactly the same as you've been familiar with for years, except now our columns aren't powers of 10, they're just powers of 2. So whereas that's the 1's place, this is going to be the 2's place, this is going to be the 4's place, and because I am only using the simplest of mechanisms to turn things on and off, electricity is flowing or electricity is not flowing, I don't quite have the same expressive range as 0 through 9. We're going to keep it super simple in this world of computers. I only have 0 or 1, off or on, false or true. And so what I'm representing right now is 1, 1, 1, because each of these lights is illuminated. Well, that gives me 1, 4, plus 1, 2, so that's 6, plus 1, 1, and that's 7. And ergo, does this sequence of 3 bits represent the number 7. So all this time inside of your computer have been any number of transistors, any number of bits. But at the end of the day, we can represent information as simply as that. Now, unfortunately, we've only counted up to, 7 in CS50 thus far. But hopefully we can do a bit better than that. And indeed we can. Suppose that we as humans just arbitrarily decided that we are going to associate numbers like 1 and 2 and 3, 4, 5, 6, 7 with specific letters of the alphabet. And for historical reasons, I'm going to start somewhat arbitrarily. But I'm going to say, humans, we are going to decide as a standard globally that 65 represents the letter A. 66 will represent B, ... 90 will represent the letter Z. And let's suppose if we really put some thought into it, we could come up with numbers for exclamation points and lowercase letters. And indeed, other people have done that for us. So now we have bits with which we can represent numbers, numbers with which we can represent letters, and with letters can we now start composing emails and printing characters on the screen. So let me invite, if I could, 8 brave volunteers who don't mind appearing not only on camera, but on the internet, to come up here and represent 8 such bits rather than these 3. So how about 1, 2? How about 3? How about 4 in light blue? 5 on the end? How about someone over here? 6 in front, 7 in front, and 8 in front as well. So I just so happen to come prepared with a whole bunch of slips of paper. And on these pieces of paper are numbers that represent what columns you guys are going to represent. So you will be, what's your name?
Analia.
Analia, you will be the 128th column. You are? Chris. Chris will be the 64's column. You are? Dan. Dan will be the 32's column.
Promit.
Promit will be the 16's column.
Lillian.
Lillian will be the 8's.
Jill.
Jill will be the 4's column.
Mary.
Mary will be the 2's, and David will be the 1's column. So if you guys could step a little forward so that everyone can see, what you guys don't see is that on the back of these slips of paper is a little cheat sheet that's about to instruct these 8 bits to either raise their hand or not raise their hand. If their hand goes up, they're representing a 1. If their hand stays down, they're representing a 0. Meanwhile, we, the audience, should be able to figure out, based on this mapping, what 3-letter word these folks are about to spell out. So in just a moment, you're going to read the first line off the back of your cheat sheet, and you're either going to raise or not raise your hand. If you're a 1, you raise. If you're a 0, you stand there awkwardly. Just like that. Go. What number, first and foremost, are these guys representing? 66. 66, right? We have a 1 in the 64's column, a 1 in the 2's column. That gives me 66. So that appears to be representing B. So you guys have spelled, okay, that's enough. B. So now let's move on to our second letter. Go. Who's quickest as math here? So 79. Again, if we add up all of the columns in which there's a 1's currently, just like we did before with the simplest of examples of 7, we now get the number 79, which according to our mapping is the letter O. So we're almost there. B, O, and lastly, go. What are they representing now? Less consensus. That's just an absolute murmur. Yes, it's in fact 87. Good. So if we now map that back up to, let's start calling it our ASCII chart, American Standard Code for Information Interchange. That gives us the letter, okay, not bow, but not bow, but bow. And that's a perfect cue for you guys to take a bow and head on back. Thank you very much. You can keep it.